Welcome back to Neural Networks Explained. This is AI Academy, and today we're diving deep into one of the most underrated activation functions, the Exponential Linear Unit, or ELU. If you've been struggling with vanishing gradients or want to speed up your neural network training, this video is for you. Before we jump in, make sure to hit that subscribe button and ring the notification bell. We post new deep learning content every week. Let's start with a quick refresher. Activation functions are the heart of neural networks. They introduce nonlinearity that allows our networks to learn complex patterns. Without them, our deep networks would just be expensive linear transformations. Think of activation functions as the decision makers in each neuron. They take the weighted sum of inputs and decide how strongly that neuron should fire or activate. The choice of activation function can make or break your model's performance. Now, ReLU has been the go-to activation for years, and for good reason. It's simple, fast, and helps with the vanishing gradient problem. But it's not perfect. The biggest issue? The dying ReLU problem. When inputs are negative, ReLU outputs exactly 0, and its gradient is also 0, which means neurons can get stuck and never recover during training. Leaky ReLU tried to fix this by allowing a small slope for negative values, typically 0.01. This helps, but it introduces a hyperparameter to tune, and that small constant slope might not be optimal for all situations. Both ReLU and leaky ReLU also don't push the mean activations towards 0, which can slow down learning. This is where ELU comes to the rescue. ELU, introduced by Clevert, Unterthinner, and Hochreiter in 2015, combines the best of both worlds. For positive inputs, it behaves exactly like ReLU, simple and efficient. But for negative inputs, it uses an exponential function. The key insight here is brilliant. Instead of a fixed slope like leaky ReLU, ELU uses an exponential decay that approaches minus alpha asymptotically. This creates a smooth, differentiable function everywhere. The motivation is threefold. First, eliminate the dying neuron problem. Second, push mean activations closer to 0 for faster learning. And third, maintain computational efficiency for positive values. Let's visualize what ELU actually looks like. For positive x, it's just f of x equals x, linear and simple. For negative x, it's f of x equals alpha times e to the x minus 1, where alpha is a hyperparameter we can tune. The derivative is equally elegant. For positive x, it's 1. For negative x, it's alpha times e to the x. Notice how the derivative is continuous everywhere, including at x equals 0, where it equals 1. Key mathematical properties. ELU is smooth and differentiable everywhere. It's bounded below by minus alpha, so activations won't explode negatively. And it approaches 0 mean naturally, which is crucial for training stability. Let's break down why ELU is special. First, no dying neurons. Unlike ReLU, negative inputs still contribute to learning through the exponential component. Second, faster convergence. The 0 mean property reduces internal covariate shift, leading to faster and more stable training. Third, smooth everywhere. This smoothness helps optimization algorithms find better solutions more consistently. Fourth, better noise robustness. The saturation for large negative values makes ELU more robust to noisy inputs. And finally, it maintains the computational efficiency of ReLU for positive values, so you don't sacrifice speed for these benefits. The alpha parameter controls how negative the function can go. The original paper suggests alpha equals 1.0 as a good default, and honestly, it works well in most cases. If alpha is too small, you lose the benefits of the exponential component. If it's too large, you might get unstable training. The sweet spot is usually between 0.5 and 2.0. Pro tip: start with alpha equals 1.0. If your network is still struggling with dead neurons, try increasing it to 1.5 or 2.0. If training becomes unstable, reduce it to 0.5. Most of the time, though, the default works great. Now, ELU isn't perfect. Let's be honest about its drawbacks. First, computational overhead. That exponential calculation for negative values is more expensive than ReLU's simple max 0x. Second, Memory usage during backpropagation can be slightly higher due to the exponential computations. Third, for very positive inputs, gradients can still vanish, though this is less common than with other functions. And finally, the hyperparameter alpha adds one more thing to tune, though as we discussed, the default usually works fine. So when should you choose ELU? Here are the scenarios where it shines. Use ELU when you're dealing with deep networks where vanishing gradients are a problem. It's particularly effective in CNNs for image classification and autoencoders. It's excellent for networks that need stable training, think GANs, VAEs, or any architecture where training stability matters more than raw speed. Avoid ELU when computational efficiency is absolutely critical, like mobile deployment or real-time applications where every millisecond counts. My recommendation? Try ELU in your deep networks, especially if you're experiencing training instability with ReLU. The slight computational cost is often worth it for the improved convergence. PyTorch implementation. Let's see ELU in action. In PyTorch, it's incredibly simple. TensorFlow Keras implementation. And in TensorFlow and Keras, it's just as easy. Let me show you a quick comparison training the same network with ReLU versus ELU on MNIST. Let's put everything in perspective with this comparison table. As you can see, ELU stands out in several key areas. ReLU is simple but can have dying neurons and no zero mean. Leaky ReLU fixes the dying neuron problem but still lacks zero mean and has a fixed slope parameter. ELU gives us the best of both worlds: exponential slope for negative values, non-zero mean that approaches zero, differentiable everywhere, and rare dead neurons. The only trade-off is being unbounded on the positive side, but that's actually good for gradient flow. This is why ELU is often called the best choice for deep networks, because it combines mathematical elegance with practical benefits. So, should you use ELU? Here's my take. Yes, if you're building deep networks where training stability and convergence speed matter more than raw computational speed. Yes, if you've experienced vanishing gradients or dying ReLU problems in your current models. Yes, if you're working on research or prototyping where the slight computational overhead isn't critical. Maybe if you're deploying to production where every millisecond counts. Consider the trade-offs carefully. No, if you're building ultra-fast inference systems or mobile applications where computational efficiency is paramount. My bottom line, ELU is one of the most underrated activation functions in deep learning. Give it a try in your next project. You might be surprised by the improved training dynamics. That's a wrap on ELU. To summarize, it solves the dying ReLU problem, provides smooth gradients everywhere, speeds up convergence through zero mean activations, and works great for deep networks. If you enjoyed this deep dive, check out our videos on other activation functions like Swish and GELU. And don't forget to implement ELU in your next project. Hit that like button if this helped you understand ELU better. Subscribe for more deep learning content, and let me know in the comments what activation function you want to see next. Thanks for watching, and I'll see you in the next video.